You're sitting still right now, reading this, motionless, stationary, at rest, except you're not. You're spinning, rotating at over 1,000 miles per hour as Earth turns. You're orbiting the sun at 67,000 miles per hour. The solar system is circling the galactic center at 500,000 miles per hour. The galaxy itself is moving through space at over 1,000,000 miles per hour. Right now, as you sit there thinking you're still, you're hurtling through the universe at speeds that would obliterate anything in your path. And you feel absolutely nothing. No wind, no force, no sensation of motion whatsoever. This should disturb you. Because if you can't feel motion at 1,000,000 miles per hour, what does motion even mean? Here's what you learned in school. Motion is relative. There's no absolute rest, no fixed reference point in the universe. When you say something is moving, you mean it's moving relative to something else. The train moves relative to the platform. The platform moves relative to Earth. Earth moves relative to the sun. The sun moves relative to the galaxy. Motion is always comparative, never absolute. You can't point to something and say it's truly at rest. You can only say it's at rest relative to something else. Fine, that makes sense, but here's the problem. If all motion is relative, then the statement you're moving at 1,000,000 miles per hour is meaningless unless you specify relative to what? Relative to the cosmic microwave background. Sure, relative to the center of the galaxy. Different number. Relative to yourself. 0. You're always at rest relative to yourself. So are you moving or not? The question has no answer. Or rather, it has infinite answers depending on your choice of reference frame. This is what Galileo realized 400 years ago. You're inside a ship's cabin. The ship is sailing smoothly. No rocking, no turbulence. Can you tell if the ship is moving? Drop something. It falls straight down. Toss a ball. It moves the same way it would on land. Every experiment you perform gives the same result, whether the ship is docked or sailing. There's no physical difference between being at rest and moving at constant velocity. Motion and rest are indistinguishable if the velocity is constant. This is called Galilean relativity. The laws of physics are the same in all inertial reference frames. An inertial frame is one that's not accelerating, not speeding up, not slowing down, not turning, just moving at constant velocity in a straight line, or at rest, which is the same thing as moving at 0 velocity. In any inertial frame, you can do physics and get the same answers. The equations work the same, the experiments give the same results. There's no way to tell if you're moving or stationary. Now think about Earth. You're standing on the surface. Earth is rotating. You're moving in a circle at over 1,000 miles per hour. But you don't feel it. Why not? Because you're not accelerating in your own reference frame. You're moving at constant velocity tangent to Earth's surface. Gravity provides the centripetal force that keeps you moving in a circle, but you don't feel that as motion. You feel it as weight, the ground pushing up on your feet. That's acceleration, but the rotation itself, invisible, undetectable from inside the rotating frame. So when someone says Earth is spinning, what do they mean? Spinning relative to what? Relative to the distant stars. Relative to the sun. Relative to a non-rotating reference frame. But what makes that frame special? Why is that frame the correct one? It's not, it's just convenient. We choose a reference frame where the distant stars appear stationary because that frame is useful for navigation and astronomy. But physically, there's nothing special about it. We could just as easily choose a frame where Earth is stationary and the stars rotate around it. The mathematics would be more complicated, but the physics would be the same. This was Mach's principle. Ernst Mach argued that rotation is only meaningful relative to the distribution of matter in the universe. When Earth rotates, it rotates relative to the distant stars. If the stars weren't there, rotation would be meaningless. You can't rotate in an empty universe. There's nothing to rotate relative to. Motion requires reference, and the only reference available is other matter. Now let's add Einstein. Special relativity says the speed of light is the same in all inertial frames. No matter how fast you're moving, light always passes you at the same speed. This seems impossible. If you're on a train moving at half the speed of light and you shine a flashlight forward, shouldn't the light be moving at 1.5 times the speed of light relative to the ground? No. It's moving at the speed of light. Exactly the same speed as if you were standing still. The speed of light doesn't add to your speed. It's constant. Always. For everyone. How is that possible? Because time and space adjust. When you move fast, time slows down for you. Distances contract in the direction of motion. These adjustments happen in exactly the right way to keep the speed of light constant. You can't tell you're moving by measuring light speed, because light speed is the same no matter how fast you're going. There's no absolute motion, only relative motion. And the laws of physics, including the speed of light, are the same in all inertial frames. But here's where it gets strange. If there's no absolute motion, and all inertial frames are equally valid, then you can choose any frame you want. You can declare yourself stationary and everything else moving. And you're not wrong, you're just using a different reference frame. When you sit in a chair, you can say you're at rest, and Earth is rotating beneath you. Or you can say Earth is stationary and you're spinning with it. Both descriptions are valid, both are correct. The physics works out the same either way. Now think about the solar system. Earth orbits the sun. We say the sun is at the center and Earth moves around it. That's the heliocentric model. Copernicus figured this out. It's simpler than the geocentric model where Earth is at the center and the sun orbits Earth. But here's the thing, both models are mathematically valid. The geocentric model is more complicated. You have to add epicycles and deference to make the math work. But it works. You can describe the solar system with Earth at the center. The calculations are messier, but the predictions are accurate. Physically, both models are equivalent. It's a choice of reference frame. Einstein took this further with general relativity. Gravity isn't a force, it's the curvature of space-time. Mass curves space-time. Objects follow the straightest possible path through that curved space-time. What we call orbiting is just following the natural geometry. Earth isn't being pulled toward the sun. Earth is following a straight line through curved space-time. And that straight line looks like an ellipse to us because space-time is curved. But here's the twist. If gravity is curvature, then falling and floating are the same thing. An astronaut in orbit is in free fall, falling toward Earth continuously. But because they're also moving sideways, they keep missing. That's an orbit, continuous free fall. And in free fall, you feel weightless. No forces act on you. You're following the natural path through space-time. No acceleration in your own frame. You're at rest in a very real sense. The space-time around you is curved, but you're following the straightest path through that curvature. You're not fighting anything, not resisting anything, just moving naturally. Now compare that to standing on the ground. You're not in free fall. The ground is pushing up on you. That's a force, that's acceleration. You're being deflected from the natural path through curved space-time. The natural path points toward Earth's center. Free fall. But the ground blocks you, pushes you upward, keeps you from falling. You're constantly accelerating upward at 9.8 meters per second squared. That's what weight is. Not gravity pulling you down. The ground pushing you up. So here's the strange conclusion. When you stand still on the ground, you're accelerating. When you fall, you're at rest. That's backwards from what you expect. But it's correct. In general relativity, free fall is the natural state. No forces, no acceleration in your own frame. Standing still requires constant upward acceleration. The ground pushing you away from your natural trajectory through curved space-time. Now let's push this even further. Space-time itself can move. It's not a static background, it's dynamic. It can expand, contract, flow. Think about the expansion of the universe. Galaxies are moving away from each other. But they're not moving through space. Space itself is expanding. The galaxies are stationary in their local frames. It's the space between them that's growing. The distance increases not because the galaxies move, but because new space appears between them. You can describe this two ways. You can say the galaxies are moving apart, or you can say the galaxies are stationary and space is expanding. Both descriptions are valid. Both make the same predictions. The mathematics is equivalent. It's a choice of perspective. But the second description is often more useful because it explains why distant galaxies can recede faster than light. They're not moving through space faster than light. That would violate relativity. They're stationary. It's the space between us and them that's expanding. And space can expand at any rate. There's no speed limit on the expansion of space itself. Now think about black holes. Near a black hole, space-time is severely curved. Objects fall toward the event horizon. But from the falling object's perspective, nothing special happens at the horizon. You cross it smoothly. No jolt, no barrier, just continuous free fall. But from far away, it looks like you slow down. Time dilation. As you approach the horizon, your clock runs slower and slower relative to distant observers. You never quite seem to reach the horizon. You're frozen there, asymptotically approaching but never crossing. Both perspectives are valid. From your frame, you fall through in finite time. From the distant frame, you never cross. These aren't contradictory. They're different descriptions of the same event using different reference frames. And here's the key insight. You're not falling into the black hole. The space-time near the black hole is flowing. It's dragging you inward. Frame dragging. The geometry itself is dynamic, and you're at rest in that flowing geometry, following the natural path, not moving through space but being carried by space-time itself. This is the deep idea. Motion isn't objects moving through space. Motion is space-time rearranging itself. Objects are stationary in their local frames. It's the geometry connecting them that changes. When Earth orbits the Sun, you can say Earth is moving through space. Or you can say space-time is curved and Earth is following that curvature. The Earth isn't moving, the geometry is. Think about it this way. Imagine space-time as a river. You're floating in the river. Are you moving? Relative to the shore, yes. Relative to the water around you, no. You're at rest in the flowing medium. The river carries you. You don't swim. You don't push. You just exist in the flow. Space-time is like that. It flows, it curves, it expands, and you exist in it, following its geometry. Motion is the flow of space-time, not the movement of objects through a static background. Now here's the part that should break your brain. There's a reference frame in which the universe is almost perfectly at rest. The cosmic microwave background frame. The CMB is radiation left over from the Big Bang. It fills the universe. It's almost perfectly uniform in all directions. Almost. There's a tiny dipole anisotropy. One direction is slightly blue-shifted. The opposite direction is slightly red-shifted. This tells us we're moving relative to the CMB, about 370 kilometers per second. That's our motion relative to the average rest frame of the universe. Does this mean there's an absolute rest frame after all? Sort of. The CMB frame is special because it's the frame where the universe looks most symmetric, most isotropic. If you could be at rest in the CMB frame, the cosmic microwave background would look exactly the same in all directions. No dipole, no anisotropy. That's a unique frame. There's only one frame where that's true. So, in a sense, the CMB frame is the rest frame of the universe. But it's not absolute, it's just statistically preferred. The frame where the average distribution of matter and radiation is at rest. You could still choose a different frame. The physics would still work. The laws would still be the same. But the universe would look less symmetric. The CMB would show a dipole. You'd know you were moving relative to the cosmic average. But moving doesn't mean anything absolute. It just means not at rest in the CMB frame. So you're sitting there, at rest in your chair, but moving at 370 kilometers per second relative to the CMB, and moving at 1,000 miles per hour relative to Earth's center, and moving at 67,000 miles per hour relative to the Sun, and moving at 500,000 miles per hour relative to the galactic center, and moving at over 1,000,000 miles per hour relative to the local group of galaxies. All of these are true simultaneously. All are valid. None is more correct than the others. Motion is relative. Always. But here's the deeply strange part. You can also say you're not moving at all. You're at rest. And everything else is moving relative to you. The Earth is rotating beneath you. The Sun is orbiting around you. The galaxy is flowing past you. And you're wrong, because you've chosen yourself as the reference frame. And that's a valid choice. Physically valid. Mathematically consistent. The universe looks different from that frame, but the laws of physics still work. Now ask yourself, if motion is relative, what's actually happening? Is anything really moving? Or is motion just a relationship between objects? A comparison of positions over time, nothing more. Maybe nothing moves. Maybe everything just exists in space-time. And the appearance of motion is how we perceive changes in the geometry connecting events. Think about a movie. Frames on film. Each frame is static. Nothing moves. But when you play the frames in sequence, you see motion. The motion isn't in the frames, it's in the sequence. The relationship between frames. Maybe reality is like that. Each moment is static, an instantaneous configuration of the universe. But when moments are sequenced, when we experience time flowing, we perceive motion. The motion isn't real. It's the comparison between static configurations. This is the block universe view. Space-time is a four-dimensional structure. Time is a dimension like space. The past, present, and future all exist simultaneously. Nothing moves. Everything just is. You don't move through time. You exist across time. Your entire timeline from birth to death exists as a four-dimensional object, a world line threading through space-time, and the sensation of motion, of time passing, is how you experience your existence along that world line. In this view, there is no motion. There are only different configurations of space-time at different temporal coordinates. An object at one time is at one position, at a later time at a different position. We call that motion, but nothing moved. The object exists at multiple positions at multiple times. We experience those positions sequentially because we're embedded in time. But from outside time, if such a perspective existed, there's no motion, just a static four-dimensional structure. Is this true? Nobody knows. It's one interpretation. It's consistent with relativity. It's philosophically strange, but it fits the mathematics. And the mathematics says motion is relative. There's no absolute motion, no preferred frame, no true rest, just different descriptions of the same reality using different coordinate systems. So what are you really doing right now? Are you sitting still? Are you spinning at 1,000 miles per hour? Are you hurtling through space at 1,000,000 miles per hour? Are you at rest in flowing space-time? Are you a static configuration in a four-dimensional block? All of these are true, or none of them, depending on how you look at it. Motion is not a thing, it's a relationship, a comparison, a way of describing how configurations change between moments. But the thing itself, the object, doesn't move. It exists at different places at different times, and we call that motion. But maybe it's just existence, stretched across space-time, present at multiple coordinates. And the motion is in our perception, not in the object. Here's the final twist. Maybe space isn't moving through you, and you're not moving through space. Maybe you and space are the same thing. You're a pattern in space-time, a configuration of fields. When those fields change configuration, we call it motion. But the fields are space-time. You're not separate from space. You're made of it, so when you move, you're not traveling through a medium. You're changing configuration. The space-time that is you is rearranging itself. Motion is self-transformation, not displacement. Think about a wave in the ocean. The wave moves, but the water doesn't. Water molecules oscillate up and down. The wave pattern travels, but nothing is displaced. The motion is the propagation of pattern, not the movement of substance. Maybe you're like that, a pattern in space-time. When you move, the pattern shifts, but the underlying space-time doesn't go anywhere. It just reconfigures. Motion is pattern propagation, not substance displacement. You think you're an object moving through space, but maybe you're a temporary pattern in the fabric of space-time itself. And when you move, you're not going anywhere. The pattern is just appearing at different space-time coordinates. Sequential configurations creating the illusion of an object in motion. But there's no object, just pattern. And the pattern doesn't move. It exists across space-time, distributed, extended, presented multiple locations, at multiple times. And you experience that distribution sequentially as motion. So are you moving right now? Depends on what you mean by moving. Depends on your reference frame. Depends on whether you think space-time is static or dynamic. Depends on whether you think objects move through space or patterns propagate through space-time. The question doesn't have a single answer, it has infinite answers. All equally valid, all equally true. You're sitting still, you're spinning, you're orbiting, you're hurtling, you're falling, you're at rest in flowing geometry. You're a static configuration in a four-dimensional block. You're a propagating pattern in space-time. You're all of these things simultaneously. Because motion isn't a property, it's a perspective, a way of describing relationships between events. And different perspectives give different descriptions. None more true than the others. The universe doesn't care if you're moving or not. The universe doesn't have a preferred reference frame. The laws of physics are the same everywhere, for everyone, moving or not, because moving and not moving are the same thing. Just different ways of slicing space-time, different coordinate choices, different perspectives on the same underlying reality. So when you ask if you're moving, the answer is yes and no. Both, neither. Depends on the frame, and the frame is your choice. Choose wisely. Or don't, it doesn't matter. The universe looks the same either way. The laws don't change. The physics is invariant. Motion is relative, and relativity is absolute. You're not moving through space. Space isn't moving through you. You and space are aspects of the same thing. Space-time, and space-time doesn't move. It just is. A four-dimensional structure containing all events, all configurations, all moments, and you experience that structure sequentially, one moment after another, creating the sensation of motion. But the motion is in your perception, not in reality. Reality is static, eternal, unchanging. A perfect four-dimensional crystal containing everything that ever was or will be. Or maybe reality is flowing, space-time expanding, contracting, curving, dragging, carrying objects along like leaves in a stream. And you're not moving, you're being carried, flowing with the geometry, at rest in the flow. Or maybe motion is real and you're genuinely hurtling through space at 1,000,000 miles per hour, spinning, orbiting, falling, and the fact that you can't feel it just means motion at constant velocity is indistinguishable from rest. All of these are true. All are ways of describing the same thing, the same reality, the same you, just different frames, different perspectives, different slices through space-time. You're not moving through space. Space is not moving through you. You are space, temporarily configured as a thinking pattern. And the pattern shifts, reconfigures, propagates, and we call that motion. But it's just space-time doing what space-time does, existing across all coordinates, and you experiencing that existence one moment at a time. Motion is an illusion, or motion is fundamental, depending on how you look at it. And how you look at it is up to you, because in the end it's all relative.